we say it cannot be something is to put parentheses around it. So it goes from -3 up to 3. It skips over 3, starts then right past 3 and goes to positive infinity. The g of x domain, Cade, what would the g of x domain be? All right, -infinity to positive infinity. So are these the same? No, they're not. The next question then says, does f of x have a vertical asymptote? And then it says, explain. Is there a vertical asymptote? Alex?
No.
Why not?
Because the power on top is larger than the power of the...
That would be for a horizontal asymptote.
Oh!
Is that right?
Oh, vertical asymptote.
Vertical asymptote.
It's no because it does cancel out. Okay.
Yes.
That's
the part. So there is not a vertical asymptote because it does cancel if you factor. So x plus 3, x minus 3 is how you factor x squared minus 9. The denominator also has that x minus 3. These cancel, leaving you with a simplified equation of f of x equals x plus 3. That piece where they cancel isn't an asymptote, but it's a hole in the graph. So this has a hole at x equals 3, not an asymptote.
okay. So I think what I had asked my question about was because I was wondering why the domain wouldn't be negative infinity to positive infinity because that canceled out, but it's just a hole.
Exactly. Yeah. So there isn't an asymptote in the graph because if you actually graph it, an asymptote, the graph needs to skim along the asymptote. So it has to go up to negative or infinity, down to negative infinity. But there still isn't a point there because that point is being canceled from the equation. And when something's canceled from the equation, it's canceled from the graph as well. So if we're crossing out a part of the equation, we're canceling that from the graph. So there's not an asymptote because that denominator no longer exists in our new function, but instead there's a hole. So an asymptote exists when a function cannot be simplified any further. So that asymptote would occur then whatever is in and remaining in the denominator. A hole is there where the portion that canceled from. So the cancellation part is literally like pulling out a hole, taking away a piece of the graph. Questions? So then if you graph it in your calculator, and I apologize, the sun is causing the picture to go in and out. It says, explain why the graphs appear to be identical. So let's talk about g of x, Brandon. What does the graph of x plus 3 look like?
It's just a line.
It's just a line.
That crosses the y-axis at 3.
Yeah, so crosses the y-axis at 3, has a slope of
1.
1 over 1, or down 1, backwards 1. So here would be g of x. We say g of x is continuous because it goes on forever. F of x also says x plus 3. And it's exactly the same, starts up at 3, slope of 1 over 1. Or down 1, backwards 1, except at the value of 3, there's a hole. Literally, there's a hole in the graph. Now, no, the calculator doesn't show it. Unfortunately, the calculator cannot draw a hole. It can't skip over a little pixelated point. But there really is a hole there, not an asymptote, but a missing point. So if we were graphing it, you draw an open circle because that point doesn't exist. This hole is at the point when x is 0, y is 6. And you can find that just by plugging the 3 into the equation x plus 3, because that's really the equation that's representing that line. So if you want to find out where your hole is, whatever the x value is, plug that in and get the y. And then that'll tell you where the hole in the graph would be located. So again, not an asymptote because there's not a vertical line going through the graph. The graph isn't skimming along that vertical line. But instead it's just a little hole that's been eliminated because we canceled. Questions? I'm sorry, the picture's going in and out. Questions between the difference of an asymptote versus a hole? So the homework looked really good. Are there questions from the graphs with the rational functions? I know 25 I was answering a couple of questions about as I was walking around. If you're not sure of the domain, or like the range, not the domain, always find the max or the min of the graph, because if there is a graph that is a parabola, you need that max point or the midpoint of the parabola to get the range, because it's going to go from negative infinity up until that point. So some of the graphs that you actually need to use the max min function to get the range, because it doesn't always go with the asymptotes. So if you need to find a max or min so that you can give the range, make sure you're using the max min function on the calculator so you can find that value. Questions? So we're going to just do the same thing today, except we're going to do the slant asymptote. We only have 2 graphs to look at, and pretty much it's exactly the same, except we'll just try and figure out how a slant asymptote is created, what it looks like in the graph. So just a continuation from yesterday. I think rational functions are a lot less work than polynomial functions, because you don't have to factor it, find all the zeros, do the long division, the synthetic division, because that's not how we find asymptotes and intercepts when it's a rational function. The power isn't as large that we're working with. Friday is your test, so we'll review tomorrow all of that rational, finding all the zeros, real, imaginary, the rational zero test, and then the rational functions. So it says, this is page 54. Okay. I got my page numbers all confused today. In addition to vertical and horizontal asymptotes, there is also called a slant asymptote. A slant asymptote is literally a slanted line. And anytime you have a slanted line, the equation of a slanted line or a diagonal line is in the form y equals mx plus b. So we're actually going to have an equation that's going to be an asymptote in y equals mx plus b form. So vertical asymptote would be like x equals 5. A horizontal asymptote would be like y equals 7. A slant asymptote will be in the form mx plus b, because the only way you get a slanted line is to have a slope. It has to have a rise over run. So these asymptotes will be in the form y equals mx plus b. 2 things have to happen for a slant asymptote for it to exist. The first one is that our equation cannot have any common factors. So the problem we just looked at doesn't have a slant asymptote because the numerator and denominator had something in common. So no common factors. Because then there isn't an asymptote if that cancels out. And I'm abbreviating numerator and denominator instead of writing it all out. So one condition, the numerator and denominator cannot have common factors. They do a slant asymptote, doesn't exist. You might not have any asymptote existing. And then the second condition is the degree in the numerator, that's that biggest power, must be one larger power or one higher power than the degree of the denominator. And only one. So if we had y equals 3x squared over x minus 1. Brandon, is there a horizontal asymptote if your equation was y equals 3x squared over x minus 1? Because?
The larger power is greater than the bottom power.
Right. So if there's not a horizontal asymptote, then there could be a slant asymptote. They will never be together. So you can't have horizontal and slant. Because horizontal asymptote doesn't exist when the power on the top is bigger than the power on the bottom. This has a slant asymptote because the degree is one higher power on the top than it is on the bottom. So that's when a slant asymptote exists. If you had the function 3x cubed over x minus 1, this would not have a horizontal asymptote or a slant asymptote. because the power is 2 more on the top compared to the bottom. So it would have vertical, but it would not have a slant or a horizontal. So specifically, one larger power on the top compared to the bottom. We are going to find it using division. Usually synthetic division works. Sometimes you may have to use long division, but we're going to divide the problem out. So as I said, just 2 examples. And they're pretty much exactly the same, except the slant asymptote changes a tiny little bit. But just going through what you did last night, how do you find a y-intercept? Chelsea?
We plug in a 0 for x.
Right, we plug in 0 for x. So this was exactly the same as last night. We're going to try and graph or analyze these rational functions by working through these steps. So a y-intercept is found by plugging a 0 in for x. And that's with any function, not even a rational function. So Chelsea, x is 0, y is 2. So y-intercept, plugging in 0 for the x's, we get 0, 2. Libby, how do you get an x-intercept?
You do that from, oh wait, that just,
So if you find an y-intercept by letting x equal 0, you find an x-intercept by letting y equal 0. And in this case, it's just the numerator. So we have 0 equals x squared minus x minus 2. How do you find x when you have x squared minus x minus 2? Alice?
You could factor that, so it'd be x plus 1 and x minus 2.
Good. So x plus 1, x minus 2. That's factored. That's the only way you can solve for x there when you have a quadratic. Got to factor it or use the quadratic formula for creating a square. But there's no way of getting x by itself, trying to move something to the other side. So Alice, your 2 x-intercepts would be
-1
and
2.
2. Good. Okay. The next one, the vertical asymptote. How do we get a vertical asymptote? Here's how do we get a vertical asymptote? Right. Denominator in this case is x minus 1, so you take the denominator, set it equal to 0. And we get x equals 1. Solve for x. So 3 different pieces get equal to 0 to find the different parts of the graph. The y-intercept, you find x equal to 0. X-intercept, you find when y is equal to 0. Vertical asymptote, you find when the denominator is equal to 0. That's when they stop them. So the horizontal asymptote is one of the 3 rules. In this case, the power on the top is bigger than the power on the bottom. That means there is not a horizontal asymptote. So just put none. Don't leave it blank. If you leave it blank, then I think you don't know what's going on with the horizontal asymptote. So write none. And then the slant asymptote is the power on the top 1 more than the power on the bottom. Yes. So we're going to divide. We're taking this and dividing it into the numerator. Usually, we kind of work through that with synthetic division because the denominator is linear, so synthetic division works. If the denominator wasn't linear, then you'd have to use long division. But I think most of the ones you deal with will have a linear denominator. So if we use synthetic division, what number would we be dividing with? Chelsea?
1.
A 1. And then you're taking the coefficients, 1, -1, -2. And we're going to divide. So we have a 1, a 0, 0, and then a -2. What this is doing is it's taking our fraction, and right now this is called an improper fraction. Improper fraction is when the power on the top is bigger than the power on the bottom. And it's kind of pulling apart the fraction and separating it. And we'll talk more about this when we get to chapter 7. But it really is taking this function and kind of separating it into fractions that would be proper and not improper. But right now, we're going to be concerned about this piece right here. It's okay that there's a remainder. We're not trying to prove that it's a 0. But what equation would be left with the numbers of 1 and 0, Brandon?
X.
Yeah, this 1 goes with x. And then technically that would be a plus 0. So this equation down here becomes our slant asymptote equation. Not the -2. So that -2 is still totally separate. It's not going to be part of your equation. It's just the remainder right now. Talk more about that later in the year. But our slant asymptote is y equals, you could say 1x plus 0 or just y equals x. I'm going to just put that plus 0 there just to remind you about graphing. Questions with that? So the slant asymptote is created with synthetic division. It's that equation that you get after you divide. There will be a remainder because we're not proving it's an x-intercept or a 0. We're just trying to pull apart and get a separate equation for this asymptote. So then, like yesterday, we have all these points. Let's graph them. So 0, 2, -1, 0, +2, 0. It's nice to have 3 intercepts. It makes it easier for graphing. And then asymptote at +1. We are going to draw in the slant asymptote as if you were making a line. So y-intercept of 0, our graph would begin at 0. The slant asymptote is literally a line that goes diagonally in the graph. The rise over run would be 1 over 1, so up 1 over 1, or down 1, backwards 1. And instead of connecting it with a solid line, you're connecting it with a dotted line because it's an asymptote. But now we have this like slanted line that's going to force the graph to go to infinity along that slanted line. It's kind of weird. Questions? So you might not need a calculator for this graph because there's 3 points. And if you can connect the dots, and know that a graph skims along your asymptotes, I think you have enough points to create a graph. So there are 2 points on the left. By definition of an asymptote, the graph skims along the asymptote and then just starts to connect with our intercepts and then continues to skim along your asymptote. So an asymptote is a boundary line. It skims next to it, goes to infinity or negative infinity. Same thing with the other one. Even though there's one x-intercept over here, skim along your asymptote until you hit that intercept, and then it kind of just goes down and follows the other asymptote.
For number 25, I plugged in the equation where I got parentheses, and that's the kind of graph that I got.
Without parentheses.
Without
Yes,
parentheses.
I think somebody else had that graph too. Yes. Can't remember who, but somebody else throughout the day also didn't put parentheses in here. They're getting a crazy graph with slant asymptotes. What would the range of this graph be? Chelsea? Yeah, this range would be negative infinity to positive infinity. Because it's going from up, like bottom, all the way up to the top. There isn't really anything horizontally that it's skimming along next to. And then the domain would be negative infinity to 1, because it's still stopping at 1. That vertical asymptote, 1 to infinity. Questions?
So the slanted asymptote doesn't affect the domain.
It does not affect the domain because it's still skimming and stopping at x equals 1. So the domain always is just from the vertical asymptote. Other questions? So why don't you try and see if you can start the next one. There's, like I said, 2 graphs, just 2 graphs to look at. Don't need to go crazy. Find the x, the y-intercepts, the vertical asymptote. So think about the pieces that have to become 0 to get those parts to the problem. Hmm?
You couldn't pick a nice numerator?
What's wrong with the numerator, Brandon?
It's not nice.
What's not nice about the numerator?
You can't just split it apart.
Yeah, this guy isn't factorable. Can't just break that up because there aren't two numbers that multiplied before that make -2. And you can't just say, oh, well, doesn't work nicely, so I quit, give up, move on. You need to make sure you have algebraic reasoning why there is or isn't an x-intercept there. So you could use completing the square, which some of you did, which is awesome. Like, I'm glad that you just automatically think complete the square. This one is a little messy to complete the square because you have to pull out a 4 from a 2. It makes it 1/2, so you probably don't want to complete the square. But the quadratic formula works. 2 plus or minus -b squared 4ac. Last year, I feel like we used the quadratic formula so minimally, and this year we've used it for a lot of different things. So, it still is pretty useful to have in your back pocket, that beautiful quadratic formula. What number is underneath the square root, Chelsea? So what does that mean then about the x-intercept? Right. So there are no real x-intercepts, and that would be your algebraic proof as to why you can say none. So don't just be like, well, I looked it up in calculator and did cross the x-axis. That's great. Calculator's telling you that, but algebraically, why? You don't have to simplify that any further. Once you know it's imaginary, you're done. So it doesn't need to be simplified. We're not finding imaginary x-intercepts. Today, yeah. So the vertical asymptote is 1 by solving for the denominator. And then the horizontal asymptote does not have 1 because the degree of the numerator is bigger than the degree of the denominator. So then to find the slant asymptote, we're going to use synthetic division and the denominator. And it's a 1 again. So that x minus 1 means you're dividing by the y value, or the x value of 1, when you set it equal to 0. And then, Michael, what's the equation that you get down here?
Y equals 4x plus 2.
Yeah, so the equation, y equals 4x and then plus 2. Doesn't matter what the remainder is. Like, the remainder could be anything. I think it's 3 in this case. But it's the equation that we're pulling out at y equals equation, so 4x plus 2. So everything that we have up here, seeing if we can graph this. -1, y-intercept. No x-intercept, but vertical asymptote at +1. No horizontal asymptote, but a slant asymptote at 4x plus 2. So the y-intercept is 2. You start there. You move up 4 over 1. That's the slope. So up 4 over 1. And this is a pretty steep line. You want to probably look this one up in your calculator. I know right here there's an intercept, so it would skim along the asymptote, hit the intercept, turn around, and come back down. Put it in your calculator to see what else is going on with this graph. How many pieces of the graph do you think there should be? 2. You won't just have 1, because you should always have a piece on both sides of the asymptote. Brandon.
And isn't it going to be like opposite over the original one?
Correct. So we have this piece here, and it's in between the two asymptotes. there's going to be a little piece that's in between the two asymptotes. If you go to your window and change your y value to like 20, you'll see that. So the evil part of the calculator is if you just look at it, you're going to be like, oh, there's just one piece. But asymptotes, there has to be a piece on both sides of the vertical asymptote. So if you only see one, change your
So they
window.
have to be like mirror images.
They're going to be very close to mirror images of each other, yes. They're not always symmetrical, but they'll be very close. You will need this point here because you'll have to find the range. So you'll need to get that minimum value. And I believe it's 1.9 and 12.8 or 9. Forget. 12.9 it looks like. But you'll need that so that you can calculate the range because you need to have that y value to get the range of that second piece of the graph. Questions? Bryn?
So do the number of asymptotes help you figure out how many pieces of the graph there should be?
In general, yes. Like if there's 2 asymptotes, then we would have 3 pieces of the graph.
So it's always one more.
In general, yes. There's always that like exception. But you could say in most cases. And like sometimes if there's not a vertical asymptote, then you would just have one piece of the graph because there's not a vertical asymptote. That vertical asymptote usually splits a graph into 2 sides. If you look at your packet, page 57, that's like part of your homework. There are 3 problems there that you're asked to graph, 2 problems to review and think about polynomials. And then there are 5 problems in the book that you're graphing. So you'll be graphing 8 problems. The other 3 are more just kind of analyzing. Fun. Tomorrow, as I said, we will review. The answers are on the back of page 57, so they're there for you to look at. And Libby, I'm working on the photo. I've had principals and IT director